right?
Yeah, it's cool.
Not for him.
I found it feels nice for me.
He's used to it.
Oh, well, maybe.
For the homework, I had the accident last week, so
What
I
happened?
lost my laptop,
Yeah?
and I have not done it homework.
Okay, yeah.
Yeah, after everything managed, I do
Yeah,
that.
yeah, yeah. So you haven't, oh, okay.
I have one homework right now.
Okay.
I have more.
Okay.
Yeah, I submitted all.
So you want, you can submit into the
Okay,
blackboard,
okay.
yeah, that's easier.
Sure.
Then I can record, because I
Okay.
haven't graded until I get, other guy also submitted everything.
Yeah,
Okay.
I have the last one, just, I have finished all.
Yeah,
of
okay,
them.
yeah,
I have just
yeah.
one last.
Yeah,
At the fall break, I had gone to the DC for my passport process.
yeah,
And while back to from DC, we had accident on.
Oh,
Bali.
in your car?
Yeah.
So you drove with some friends? Or?
Yeah,
Oh.
I had gone with my friend from engineering department.
Okay, so what happened? Yeah.
Bus was crashed, and luckily we saved.
Oh, so some people got really bad injured?
No,
No.
for the driver, he got some injuries in his forehead.
So this was a Greyhound bus? Or? No,
No, in a personal car.
personal, okay.
Yeah.
Oh boy, that's scary.
Yeah. At that time, I lost my laptop.
Laptop.
That's why.
So you lost or you damaged?
Damaged.
Oh.
Yeah. So,
Can you recover? Hopefully.
That insurance will cover.
Oh, okay.
Yeah, that will not damage his badly damaged.
Okay, hard drive should be okay,
Yeah.
right?
So
Yeah. Make
that's
sure
why I'm behind. I have not graded
Yeah, that's
anything.
fine, yeah, yeah.
I will grade all the homework. I have
Yeah.
not grade. I think I am 2 weeks behind.
Okay.
Yeah.
Yeah. So now I think you, these two submit in the one, so I can
Yeah.
grade the homework and you back you. I will do it this weekend. Any question with new homework? Graphene one is very simple, don't.
Okay.
I think question 1 is easy.
One is very easy.
Yeah.
So 2 is graphene one. I think it looks pretty complicated, but if you look at it, it's very simple, right? So it's your energy for the graphene one is given as some constant time, then k squared plus k, because this is 2-dimensional, right? So basically this means really k, right?
Yeah.
K squared is k squared plus ky squared. That means this e k you can write as whatever the constant times k. That's it, right? So now you know what is dE over dk. Just simply this one. So then it becomes so easy to calculate that. Then everything else is same. Your number of electrons is given by 4 pi k squared dk divided by 2 pi over L squared, right? From here you get your nk. So then from here you get dE over dk. Then you can easily calculate ne. That's easy, right? So then second part is little bit difficult. You have to calculate the total number of electrons, right? How do you do that? That is basically, you know, dN is basically your this density of state, whatever this Ne, dE, but it should be multiplied by your Fermi distribution, right? So this means you have to integrate from 0 to infinity. So we know density of state from here. You know Fe. Let's do that integral. Very simple. It looks difficult.
Yeah.
Maybe the integral, you may have to look at some integral table. Let's get started. Where is everybody? Well, don't come on time.
you in the hospital in Maryland?
At that time, I was good.
Okay.
Nothing bad happened at that time, but due to time passes, I feel some pain.
Okay, let's get started. So last time we started introducing the potential, right? So in the Schrodinger equation, what potential we used? We used this u equals some u0 plus u1 cosine 2 pi x over a. This kind of periodic potential, right? When you do this one, we look at different conditions. So especially we are interested in the situation where k equals pi over a. That means your pi over a means the your brilliance on boundary, right? If you look at your k, so we know your brilliance on boundary is pi over a, right? So in this situation, actually you see your this wave function, right? If you write your wave function kx minus omega t, that wave will always get reflected back from the brilliance on boundary. So that means you write your wave function as either, you can write, what is the wave function moving to right? Usually you write ei kx minus omega t. Then you have one moving to left. Here you should have negative, right? Basically. So plus or minus be minus I kx minus omega t. So depending on this plus or minus, we define two wave functions. So actually that means actually you have two. What you get if you have one wave moving this way and another wave moving this way, they are going to interfere, right? So then we get something called standing waves. So you get two standing waves, that's the important thing. Two standing waves. So we call one psi plus. That means when you have plus sign here, that we write as, actually in this situation, this A and B both are equal. We call that one C. Because this is a strong backscattered at this pi over A, right? You have the same amplitude. So then you write one as, say, C E I kx. I'll write E minus omega t here. We don't have to worry about that time dependence part. You have this one. First I'll write plus 1. Same C E minus I kx, right? This is one wave. I call that, this is the standing wave, please remember. Psi plus. Other one I write as psi minus. That means you take this minus sign. So that means C E I kx minus E minus I kx. This one. We don't have to worry about the time dependent part. So now we have two standing waves. These are two standing waves, right? So if you know this standing waves, we can find what is the, these are quantum mechanical wave functions, right? So we can find what is the probability function. What is the probability you can write for the psi plus, you have psi plus star times psi plus or psi minus star times psi minus, right? You have two ways of this electron localizing in the crystal. So standing waves means what? If you have a standing wave, suppose something like this, you have some positions. These are, we call the antinodes, nodes here, or antinodes. These are stationary points, right? They don't move. That's why if you look at stationary wave, they, at a given time you have a specific shape there, right? So those are, like if you take something like this, we know this point they are always moving up and down, right? But stationary waves, they are localized, is a stationary points. That means depending on this wave function, your electrons will be localized at certain points, and this, according to this one, they will be localized at different points. So that's what we are going to discuss here. Just imagine if you take this psi plus, that means this one. So don't worry about that's a normalization constant, that 1 over square root of 2, doesn't matter, that one. So now if you write this one, psi plus, this one you can write as cosine x, kx, right? You know cosine kx is given by e kx plus e minus kx. So that means I can write this function psi plus as, this is correct, right? Cosine kx. Then how do you write the probability function? If you take the star, then minus become plus, they cancel off this, you get cosine squared kx. So that means your probability is cosine squared kx for the psi plus wave. Psi plus stationary wave, you get, this is proportional to cosine squared kx, right? So that means you get maxima when your kx is what? Maximum point you get when kx equals 0 or pi or 2 pi, like that, right? N times pi. That means you get x is, x is, kx is, but here we, that's fine. So you get kx equals n pi positions. So now, that is for the, just calculate the, this is what we are calculating is psi plus star, psi plus, right? This, the probability. So now if you write this one, so you get 2, square. So here k, you get k, what did we write here? K is actually pi over a, right? So when this happened, this is the important thing. We wrote this equation like c times ae minus kx plus ei kx only when k equals what? Pi over a, right? That's the important thing. So that means I can write this probability function as cosine squared pi over a. K equals pi over a, presumably. That means you get the maxima when pi x over a equals 0, pi, 2 pi and things like that, right? That means x equals what? X equals 0, your pi cancel, right? 1, 2, like that. So x equals either 0, 1, 2 times a, right? That means 0 or a or 2a, like that. So what this means, if I take my atoms like this, so this is 0, then we have a. So that means your wave function maximize at this point, right? That means basically cosine squared means basically your cosine is like this. So this part also becomes cosine squared, right? So that means this becomes maximum at 0, a, 2a, 3a, like this, right? At the atomic position, these are atom position, right? Here we are talking about the electronic wave function. The electrons are localized where? Right at the ion position. So that is for the psi plus one. How about the other standing wave? That is eikx minus e minus ikx. What is that? That is sine, right? I times sine kx. So that means, you can see here, that is, if you write second standing wave, so this one you can write as 2ik, because sine 2x is e this one divided by 2i, right? So this means this one. Now if you take the probability function, if you do this one again, this cancel I squared, you get sine squared. So according to this one, sine squared pi x over a, right? So this one becomes maximum where? When this angle is 90 degrees or 270 like that, right? So that means you get when pi x equals 90 or 3 pi over 2 and things like that, right? So that means x equals what? You get x equals a by 2, 3a by 2, 5a by 2 like that. That means your electrons now will be localized where? The center of the two atoms, right? A by 2. That means you have maximum comes here like this. This is where? This is a by 2, right? 3a by 2 like that. You can see how depending on these two standing waves, your electrons will be localized like this. First one localized, this one localized when x equals a 2a 3a. Second one, this one localizes when they are in the middle of the atoms. Is that clear? Because sine squared versus cosine squared, right? So because that has the highest energy, because your energy is minimum at the position, right? Because we know energy is minimum at the atomic position, right? Like this is where the minimum potential energy. So if you look at the picture, this is how it looks like. See, this is the psi plus star psi, right? So they maximize exactly at the ion position. So other one, this is psi minus star psi minus, that's maximized right at the middle, a by 2. So that means you have these two standing waves corresponding to this where the electrons will be localized. Now if you know the wave function, you know the probability function, then you can find what is the energy related to that each wave function, because always we have this Schrodinger equation relates to your wave function and the energy, right? So how do you relate the energy? For the first one, we will call this energy as, say, E1. How do you calculate E1 energy? So E1 comes from the psi plus wave function. So that means that should be psi star, psi plus star, right? Times your potential U times psi plus, this is a one dimensional case. If it's 3 dimension, you have to do this one, right? In the other energy related to the second wave function, that will be psi minus star times U, that's your potential, times psi minus. So you can easily calculate these two because we know what is U. What is U? U is given by that U0 plus U1 cosine pi over pi x over a, right? So now you can calculate the two energies. So in this one, instead of calculating E1 and E2, I will calculate the difference between the two. E1 minus E2, I can easily calculate that one this way, right? E1 minus this we call, actually they call it E minus. This is E minus, this is E plus. So how do you calculate the difference? This is fine, right? If you take U out, is that clear for everybody? So I am directly calculating the difference of those two energies. E minus, this is the probability function coming here. Now you know how to do this one. Ux is given by this one, right? Forget about that first term, that's a constant term, right? U0 term. What is important is this one. So now we know that one is cosine squared, right? This term is sine square. Is that clear? So now that's it. You just easily calculate. You have to only calculate x going from 0 to a because it repeats, right? Okay, so if you do that one, you know how to write this function. Cosine squared x minus sine squared x is cosine 2x, right? So that means here this by this 2. If you substitute that one, you get that difference is that's what you get, right? The cosine squared minus sine squared, you write that 2 times this one. So now this one you know how to integrate, right? Cosine squared. Either you can write as like cosine 2x and integrate like that. You know how to do this one. If you write this way, just please go ahead and do. So when you do this one, you get another cosine squared is cosine 2x is 2 cosine squared minus 1, right? So then you get 1 plus here. Then again 2 comes here, right? 2 theta. If you do this one, please go ahead and do this one. If you do this integral limit, you get answer as minus u1. So the u1 was this one, right? U is u0 plus u1, this cosine pi x over a. So that difference between the energy is simply what? That the potential function, right? Amplitude. So that's pretty neat. So we call this one, actually, if you look at this now, the dispersion curve, it looks like something like this. So previously, when you didn't have any periodic function, so when you had the zero potential, free electron gas, what was the band structure? This one, right? No discontinuity. So when you had basically K versus E. So free electron model we got is basically this is going to infinity, right? So now we introduce the potential. When you did that one, we got some discontinuity here at this pi over a minus pi over a plus pi over a. You get this, at that point you got 2 energies. So that means you have actually something, this is what we call this free electron one. So now you get 2 energies at this point, one, then other one is different. So this is a E minus, then you got this one E plus, right? So they continue like this. Same here, you get E plus at this point, then you get E minus like this, then continue until later when you go to 2 pi over a and minus 2 pi over a, that's the second Brillouin zone, right? At that point again it will open up some this. So this is like E plus for the second Brillouin zone, this is E minus for the second Brillouin zone. Don't worry about that one, only look at the first Brillouin zone. So in that one you will see, this is what the free electron theory. Now you have, at this point you have one energy E plus, another energy E minus. There's a discontinuity here. So that means there are no states available in that energy range. So in the free electron model, remember, all these states are available. So typically we have, suppose EF is here, Fermi energy. Up to this point all the states are filled. All the states here are unoccupied, but these electrons can occupy that one. But in this case, you get situation, you have some energy range. In that one, no states are available. These are completely unallowed. So that means if electrons are, suppose your Fermi energy is here, these are filled up to this one. So then where would the other electron go? No state, right? You don't have any other states here unless you have enough energy to go to this state. We call this one as the energy gap. There are states, there are no allowed states for that electrons to be there. So we know that Eg is what? Basically minus U1. We showed that one because U1 is a negative number, right? Remember when I wrote this function U0 plus U1 cosine pi x over A. So when you write this one, your U1s and U's both are negative numbers. So that means your energy gap is a positive value. Is that clear? So that is very important thing. This is the origin of band gaps. Otherwise, if you use the free electron gas, your complete band structure is all states are available, right? Now you can see, so you have only states up to here. After that, no states here, unless you can overcome this barrier and come here. If you take semiconductors, this band gap is very small. It can be maybe 0.1, 0.2 like that. So even simple, even at room temperature, kVt value, right? Your T is 300 K. Even that is enough to promote some electron from here to over the gap, if the band gap is very small. But if the band gap is very large, say insulators, like diamond like this, it's very hard to move one electron from this band to next band. So now let's look at, separated by this one. So now if you look at any textbook, so you will find different this band structure representations. In some books you will, so this is clear for everyone. This is the simple the free electron gas theory. So then if you go, this is the first Brillouin zone, second Brillouin zone, and so on. We already talked about if you are beyond your first Brillouin zone, you can, with same by G vector, with the G vector we can fold it back to the first Brillouin zone by subtracting plus or minus G, right? If you are here, suppose at this point, I can subtract G vector. Everybody remember G? G is simply 2 pi over A times N, right? So that's the translational vector in the reciprocal space. This is a reciprocal space we are talking about, right? If I am here, I can move that one back to first Brillouin zone to this point here. So this is the first Brillouin zone, right? Just look at this point. This point by G is this much, right? You can bring it down to here. If you are here, you can bring it back to this point by subtracting G, right? So if you are here, this part you can bring back to this one. Can you see here? This part can brought it to here. So this part, anything here, that is this one. Just subtract G vector. So if you do that, this is this is a free electron, the band structure. When you have the periodic function, your band structure becomes like this, right? The way I drew this one. You can continue this one. We call that one as the extended zone scheme. You can extend this one, right, for all the ones. So then, by folding this one, we talk about everything in the first Brillouin zone. That is we call reduced zone scheme. So this is, we reduce everything back to first Brillouin zone. Also everything happens in the first Brillouin zone. If you continue in every Brillouin zone, like this is the first Brillouin zone, you have this one, same thing continues in the second Brillouin zone and third Brillouin zone, like that. So that one is called the periodic zone scheme. If you look at textbooks, they can represent your band structure in any of these ways. So here, this is called the extended state. Everything in here we call the reduced zone. If the reduced zone is repeated in every Brillouin zone, we call this the periodic zone. These are the three ways of doing that one. See, any vector can be brought to the first vector just by adding or subtracting g vector, right? For example, if this is here, I can bring this point to here, right? This part becomes this part. This part becomes what? This part, right? Is that clear? This is important to understand. If you especially read articles, so you need to know which kind of structure you are going to look at it. Okay, this explains that. See, this is what I was talking about. By subtracting g, you can get into within the first Brillouin zone. Okay, so now look at this one. So suppose you have a monovalent atom, say lithium or sodium. So then you know if you take the states, so each state can support how many electrons? 2, right? Because spin up and down. So that means if you take a monovalent electrons, up to half of this one is filled, right? Why half? Because each one can be 2, right? So that means if you take monovalent, so your Fermi energy will be exactly at half, right? So up to here it is free. So that means these are still available unoccupied state. That means these electrons can always occupy this one. That means it's a metal, right? That's correct, right? So now let's look at, it's a divalent metal, say something like magnesium. If it is divalent, states are completely filled here, because divalent means you have 2 electrons, each one can support 2, that means it will fill all the states, right? So then what do you have? After that you have band gap, no states available, right? That means what? This one cannot have any electron. That means divalent metal should be insulated. Is that correct? We know it's not true, right? Magnesium is a metal. So how do you explain that? Is this clear? If you have monovalent, it is filled half, right? So then you have enough states. That's good. So they can promote, that means it's a metal. But if it's a divalent, it's all filled up to this one. So then no states here, should be insulated, right? What is wrong in that picture? That's what you expect, right? Actually, if you take any these metals, so it's not exactly like this. So this is what I was trying to say. This is clear, right? Only one valence electrons, so that means it's half filled, right? So up to here. So that means it is, you have unoccupied state, that's fine. So if you have a divalent, yeah, so does this mean divalent element will always be an insulator? It's not true, right? But its opposite is true. If you take any insulator, they are divalent, but not divalent metals are, elements are insulator. Reason is, if you, so this is the insulator situation, right? So it's filled up to here, no state here. But if you take any metals, if you look at in the different direction, because this is your K direction, right? You can go in the direction of say 1, 0 or 1, 1 direction. If you go in different direction, it's not just like this. It can be this kind of band. That means there are states available for these electrons to go here. So that means there are in different directions you have overlap of these bands. So if you look at this energy, these electrons can go to this band because this band is not like this. There's some overlap. So even at this energy, is that clear? That's the reason why dimetal elements are not insulators. If you assume the perfect, this kind of band structure, it should be insulating, right? But you have this overlapping bands. So then also in some cases you can have this something called the semi-metals. You have some electrons states available in this band. So please remember, it's not divalent elements are electron, but this is true. Even number of valence electrons in a primitive shell can be insulators. So if you take insulators, it will be mostly the integer number of like 2, 4, 6 like that. But opposite is not true. Is it clear for everybody? Yes, sir. Okay, so now let's look at the this bands and the Fermi surface. Everybody remember the Fermi surface in 2D materials. So this is my reciprocal space. Then I know how to draw the all my brilliant zones, right? First brilliant zone, everybody remember? That's basically the weakness side cell, right? If you draw that one, you can have this is my first brilliant zone, right? This is my second brilliant zone. Then I have third brilliant zones like that. So we talk about that one, right? So this basically bisecting closest, next closest, and the next closest, and like that. And that's how we calculate the. So you can see, yeah. So now I think I have put the labels here. Here's the first brilliant zone. Here are the second brilliant zones. Here are the third brilliant zones. So now let's look at how the Fermi surface looks like here. What is the Fermi surface? So let's do it for a two-dimensional case. Fermi surface is given by what? Typically, this K space, right? So this is your Kf. This gives you the Fermi, the circle in this case. In three-dimensional, it's a Fermi sphere, right? So now how do you calculate Kf? If you remember, number of electrons is given by, this area is given by what? Pi Kf square, right? Divided by each state is given by 2 pi over L times square. That will give, actually this is half of this one. Why? Because each can be 2 electrons, right? So if you do this one, what you get? L square becomes A, pi, and one of this pi cancelled. So that means you get A times K squared divided by, here you have 4, right? 4 pi, right? And here I have 2, then 2 and 2 cancel. That means I get n equal A K squared divided by 2 pi. Now K squared is given by 2 pi. N over A I can write that simply. So N means electron density, right? In this case, N means N divided by A. If it's a three-dimensional case, N is N divided by V, right? So that means Kf is given by 2 pi square root of N. So now if I draw my Fermi surface, depending on A, my radius will be different, right? If you take monovalent metal, so N is in that scale, say 1. So if you take divalent, N will be 2, right? Because it's not exactly 2, because I'm talking about how it scales out, right? If you take trivalent, that will be 3. That means if I draw my Kf, this is Kf, right? For monovalent is something like this, right? Divalent it will be bigger, right? Trivalent it will be much bigger because that scales with n. So that's what we are going to see, how that one fits in this first brilliant zone. If you take, just simply take here. If you take 1, n equals 1, so your Fermi surface will be something like this, right? If you take 2, it will be something like this. This makes it very complicated because it cuts the brilliant zone, right? If you go to 3, it will be like that. If this happens, again we have to do this folding business. So this is what, in the first case, you don't have to worry about anything, right? So you will do one homework problem to do this one. So this is my first brilliant zone. So in the first case, this situation is fine, right? So all the electrons are within that first brilliant zone. But if you go to divalent, it becomes something like this, right? If this happens, you can fold it back. So this part, if you subtract G, you will find this one exactly comes like this. Here this point becomes this point, like that. This part, you can fold back to like this. How about this one? That will comes like this one. Then this part, subtract G, then this will be like this. Then you will have something like this. Okay. So now if you go further, you can do the same thing. So then you can bring it. So even if you have like this, how do you do this one? This part also you can bring it here. This part you can bring here. This part you can bring here. This part you can bring here. That you can always fold it back to the first brilliant zone. I will give some homework problem to play with that. So especially in this case, in the divalent case, this is how it will look in this reduced zone scheme, right? So, but this is without any periodic potential. When you have the periodic potential, this becomes slightly distorted. It distorts so that this becomes kind of perpendicular to this brilliant zone boundary. This is more like, that's because of the this becomes this curving thing happens because of the periodic potential. Otherwise, it's smooth curve, right? Okay, you can see that one. Yeah. Okay. So then, so we'll get back to that one. Next, one thing I want to talk about when you have this band structure. Let's see how many of you can understand the density of state of this one. So if I have this one, suppose then I have one like this, right? This is E. Yeah, but this is more like the band gap, right? So now if I draw the density of state, how does it look like? If this is my density of state versus E versus NE. How does the density of state, let's do from here. Yeah. This is density of state as a function of E. How does it look like? For three-dimensional case, what is the density of state? Goes square root of E, right? So that is something like this. Right? If you draw, let's do this. Yeah, this is my energy, right? Yeah. So this is my energy. This is my density of state. Yeah, that's the easy way to draw it. If I draw my density of state, you remember square root of E looks like this, right? So this is fine. So your density of states are here. At this point you get something. What is the density of state here? Are there any states there? So here's density of states should be 0. That means this goes like this, then it should come to 0 like this. So that's how density of state, typically your density of states look like square root of E function. But if you have some band gap, it should come to 0. It doesn't come immediately 0. It has some discontinuity and comes to 0. This is how your density of state should look like. So here you have the square root of E function. When it comes to here, it should come to 0, right? But it comes with some discontinuity. Then 0 here, right? Nothing here. Then you have again until you get to the next. Suppose this is my second brilliant zone. So then it comes here again. You have this square root of thing. Then when it comes here, it should come to 0. Right? Then you have another 0 density of states. Let's try to understand. So whenever you have band gap, that means your density of state becomes 0. Density of state means number of states, right? So there are no density of states here. It's 0. So this is how you will see a lot of pictures, diagrams. You have this kind of density of state. You have like this, then. So that means at this point, density of state becomes 0. If you have a band gap or something, right? So here is another way you can show density of states. So I just draw the density of state if I with the dark areas. So in this part, these are two different directions. Here, this go in the 1, 0 direction. Here, this is in 1, 1 direction, right? The band diagram doesn't have to be in the same direction, right? If you go from gamma to X or gamma to L, so there's different directions. So here, can you see this is dark here? That means I have electrons here, right? That means density of state is finite. How about here? 0. That's why there's nothing here, right? Then up to here, you can see all the way filled. So if you look at this side, up to here, it's all dark, right? So then how about here to here? There's nothing, it's 0, right, in that direction. Then from here to here, you have electrons. So that's another way to represent how the electrons are filled in a band. Is that clear? Or if you can draw this one as density of state, I can draw this one like this, coming to 0 here, then again 0, then this is going until you get to this one, right? Either way. Here, how the density of states, draw this one, the square root of E, then goes to 0 here, right? Then 0 here and so on. It's very important when you read some papers, you need to know how they should be here. Yeah. This is what I was trying to explain to you over there. How when you have this periodic boundary condition, how the this bands we are going to fold it back to first brilliant zone. So you can see everywhere this will be like plus the perpendicular to the brilliant zone boundary. So this is for a different two-dimensional gas, so that's different one. But important thing is this, you can see this always that Fermi surface becomes normal to the brilliant zone boundary. So the simple case is like that, right? So that is for two-dimensional case. In the three-dimensional case, you can imagine how complicated that can be, right? So, and you don't have to remember it. Okay, so now actually I want to, so we talked about all these bands, like I said, going from gamma to these different symmetry points, how the band looks like, right? But this is coming from some kind of computational technique, so still you can understand how the band looks like, right? So here at this point you have this discontinuity coming here. You can see that's where we have the band gap, right? Here again you can see the band gap. So, but this is little more complicated way of doing rather than the simple potential term. There are a lot of ways to calculate the band structure. I will talk two more techniques, one called the empty lattice approximation and one called the tight binding models, so how to create the band. So what we did was very primitive, right, very simple way. So I will talk about how to calculate this kind of band structure using especially the tight binding or empty lattice approximation. So when you do this one, I think we talked about this one, but everybody should remember this notation here. So typically, if you take two-dimensional case, you have this, always gamma point is the center point, right? So then, always if you go in the 1, 0 direction or 1, 0, 0 direction, for say in two-dimensional case only 1, 0, right? 1, 0 direction where it intersects the first brilliant zone is called the X point. So typically 1, 0, say two-dimensional case, 1, 0 direction, you get X point. If you go on 1, 1 direction, we got the L point, right? So if you start from gamma, if you go 1, 0 direction, this one, right? Where it cuts is X point. If you go in 1, 1 direction means this way, right? So where it cuts, that is the L point. So this can be extended for simple cubic or FCC or BCC. So especially if you talk about BCC, so typically FCC I have red color, BCC I have blue color. So X is more like 1, 0, right, in 2 dimension, but in 3 dimension is usually 1, 0, 0 direction. If you go on 1, 0, 0 direction, where it cuts the point is called same as X point. If you go in the 1, 1 direction, is basically like L point, right? So just like in the 2-dimensional case, but it is mostly that is called for the FCC. So in the BCC, there are these names. You can see this one. If you go on the 1, 0, 0 direction, the intersection point for FCC is called X. For BCC, it is called H point. So in the 1, 1, 0 direction, so this is FCC has K point, BCC has N point. So same here, L and P point. So here you can try to understand. This is FCC, gamma point, to if you go to say 1, 1, 1, this is 1, 1, 1 direction, right? So you get L point here. Here you get 1, 1 direction is P point here. So if you go 1, 0 direction, that is this direction, right? So if you go this way, you get either H point or X point here. This is the boundary. If you remember this one, is very easy to remember how that should be. So then also you can go for the simple cubic one, also very similar thing. From gamma point to, you can see 1, 0 direction X, and it may be slightly different. So these are the points. Then the direction or the line is called this delta, sigma and gamma. So going from gamma to x, gamma to say x, this length, this direction, or that the direction mostly is called the delta. If it is always measure from gamma to k, that is, if you go from here to here, this is called the sigma direction. If you go from gamma to L, that means if you go from gamma to L, this is called that is gamma, right? Yeah, sigma, delta, sigma, and gamma. These are directions. Please remember this one. Directions are basically gamma, sigma, and delta. These are points, right? Gamma, and then X, L, K, these are all points. So what did I say? This one is what? It's a lambda?
I think it's gamma.
So this is gamma, right? Okay, so those are directions, yeah. These are points. So these are all points. These are all these are directions. So this is useful when you read some literature. So then if you take some of these metals, you can see the band structure going from gamma to X, so gamma to L, whatever. So you can see how the bands, so whatever the scheme, right? So then if you look at the density of state, these are very important. If you look at your typically metals with different electrons, right? You can have S or P or D. So typically, if you work on like transition metals like copper or iron or nickel, cobalt, they have d orbital electrons, right? Those electrons have much higher density of states. So typically, if you take density of state versus energies, so your p-s orbitals, usually they have this square root of E behavior. But if you go to d orbitals, they have much higher energies, right? So that means this energy is also density of state is much larger. They usually have this large band for the d orbitals. S orbital, they have low energies, they have much smaller density of states. D orbitals, that's why they are useful for catalysis and things like that. They can occupy more, like higher density of state, because they are at higher energies. So this is another important. So you can see this D band, and maybe these are for S or P orbitals. Certain things you should try to remember. So this is the Fermi surface in 3D. So that's pretty complicated, right? Okay, so next we go through another way to create the band structure using something called Bloch's theorem. This is the most general way of representing electrons in solids. So still, whole idea is to solve this equation, right? So we know how difficult to do that one for a given potential. So that's why the Bloch's theorem, so that actually started from this Flockert. So he developed this one for the one-dimensional case. So then later Bloch generalized it to three-dimensional case. So whole idea is to find some wave function. So that way you can get the, once you know the wave function, you know how to get the energy, right? So if you know the potential, you can easily get that one. Finding the wave function is the hardest part. So Bloch's theorem is, so that means we call the Bloch wave function. Each electron can be represented by some wave function, as saying one-dimensional case. So this K represent that state, right? For given. So Bloch's theorem is this. In order to solve this one, you have to assume your potential has some periodicity. That's the first thing. So you have to say you are, if you add your real space translational vector, you get back to you are. So this is your potential. If your potential has some periodicity like that, that's reasonable thing to assume, right? Your potential has some periodicity. Then Bloch said your wave function that you want, right, to represent the R, that should have the periodicity of this U and another. So this will have this periodicity of your U times your the running wave with this kind of running wave function. So basically you should have this periodicity. So we know T what that one is. So yeah, sorry. So there are two ways of writing this. This is what Bloch's theorem is. So for a given state UK, then this should have UK. So that same K is representing this running wave. Your wave function will have term that has same periodicity as the potential plus a running wave or periodic wave. That is the Bloch's theorem. So this is what says potential is invariant under translational vector. That's reasonable for a crystal, right? So the T, everybody remember T? These are A, B, C are the basis vectors. So U, V, W are integers. So then you write the wave function for this Schrodinger equation. This U has this invariance. Then you can write psi as that same function periodicity as this one, right? So this UK has same periodicity as your function times E k dot r. So this doesn't have to be that same U, any function. So this U, this one has the same periodicity as this potential term. This is product of two parts. One part is simply running wave solution. Other part is some function that has the same periodicity as your potential. That's all. So Bloch showed that the solution to the Schrodinger equation are the product of a plane wave, that is the plane wave here, right? And a function with the same periodicity of the lattice. Is that clear for everybody? That's the Bloch's theorem. Just very simple, we can use this one. This we call it Bloch function. So this one should have the same periodicity as this one. Is that clear for everybody? So this is the starting point. So now, yeah, so if this is the case, this function will have the same period. So this is potential, this is any function. The UK is basically any function, only thing is it should have the same periodicity as this one. Two parts. Function 1 is the periodic wave. This UK should, this one UK R should be same as UK R plus T. The same periodicity as the potential periodicity. So that means if I write Bloch's theorem, psi k R plus T is what? If you write this way, UK R plus T means UK, sorry, if I write that is psi k R plus T is what? R plus T means everywhere R I replace with R plus T, right? So if you do that one, psi k R plus T becomes UK R plus T. This one I can write as IKR times E I T, right? That's basically this one. Is that clear for everyone? So now, according to Bloch's theorem, this one is same as this one, right? UKR plus T is UKR, that's the condition, times EKR, this one. So that should be clear, right? So that's basically, so if you do this one, you get, what is this one? UKE, that is basically UKR was psi KR UR, IK dot R was simply psi KR, right? So this one I can write as psi KR times EIK dot T. So this is another way of writing Bloch's theorem. One way to write Bloch's theorem is this one, right? Psi KR is UKR times EIK dot R. Or you can write psi KR plus T as psi KR times EIK dot T. Yeah, exactly same. You can write your Bloch function this way or this way. Psi KR plus T equals psi KR times EIK, here the K dot T. So that is same as, so they both are identical thing, right? Is that clear for everybody? So there are two ways of writing Bloch's theorem. If you know the periodicity for any time, if you want to find your this one at R plus T, you just write as this psi K simply R times EI, that's K dot T. This is the second way of writing that one. The derivation is easy, right? It's same as. So, yeah, this is what I wrote here. It is easy to show that this equation formally implies Bloch's theorem. So if you want, you can easily do this proof why they are same. So that means you have to prove this one, right? In one dimension, R plus T is what? X plus, this is A, right? T is A. X plus A equals psi K X times EIKA. That's what you have to show, right? This is what you have been. This is 3 dimension. This is how it looks in 1 dimension, right? Because T means some A, right? So then psi X. Yeah. How do you prove this one? Just use simple the boundary condition thing that we did before. If you remember doing this one. In this one we know psi X plus NA, and that is psi X, right? N plus 1 becomes psi 1. X plus N plus 2 becomes X2, right? That's what this one means. So that means X plus NA is simply psi X. Now you can do this one for psi X plus A equals psi X EIKA. Then psi X plus 2A is what? Psi X plus A times, again, so you can do it like, yeah, let me show you. I don't know whether you get this one. So if I write, say, psi X plus A equals some constant times, say, psi X. So then I have to show C equals this one, right? That's what I have to show. If psi X plus A equals some constant times psi X, then what is psi X plus 2A? X plus 2A is what? Psi X plus A plus A, right? So that means psi X plus A is simply, so that means you can write as C psi X becomes now psi X plus A, that becomes C times psi X, that means C squared psi X. If you go to psi X plus 3A, do this one, you get another C, that means this become C3, right? Just follow this one. Anything x plus a, you can write as this one. That means psi x plus this one plus a means, so simply psi x plus a, c times psi x plus a, psi x plus a is c times psi x. That's how you get c squared like that, right? That means if you write cx plus na is what? C to the power n times psi x, right? Just write, start from this one, then write what is psi x plus 2a. So, get it? Yeah. So if you do that thing, so you get easily psi x plus n is basically c to the power n times is psi x. So we know that one equals boundary condition, so that is simply psi x. I don't know whether you should do this yourself. It's just simple. So if you do this one, so now psi, so if this is the situation, Cn equals 1, right? Cn psi x, that means this is, you can write as 1, you can write as e I 2 pi n, basically, right? So that means you get n equals, so yeah, Cn equals 1, yeah, so you can write that 2 pi ni here. So n equals any of these, so that means c equals basically, you have to take 1 over n function here. That means c equals e I 2 pi n over n. You have to take 1 over n, right? Yeah. That means what is this one? I can write this one as Ka. If you write this one as 2 pi n over n is Ka, so then you get K equals 2 pi over Na times n. That's what we were supposed to prove, right? 2 pi n over Na is actually the length L. Now this just will prove it, yeah. So that means C is basically Ei Ka. K. 2 pi over Na we write as K. That's the proof. That's not necessary, just to show it. So basically what I want you to understand is this one. For the Bloch's theorem, please remember this one. The derivation is very simple. So your Bloch theorem is psi k r equals some function Ei k dot r. This is the Bloch wave function. Only thing is this UKR should have the same periodicity as your potential periodicity. Your potential U also had the same periodicity as R plus T. Right? So then this one you can easily write in a different way. Psi k some R plus T as your psi k R times E I k dot T. K dot T is basically that. So in one dimension, how do you write this one? Psi k x plus a equals psi k x times E I k a. That's it. So that's what it is. So we'll use this one in one example. Please remember, it's very important to remember this one. Let's do one quick. This is almost time. So now let's look at what this wave function means. So suppose your potential or your psi k is this psi k, you need to have some uk, right? That should be periodic. That means at each lattice point, if you take this each lattice point, you should have the same function, right? It can be something like this. With same periodicity, if you go from x to x plus a, you should have the same periodicity. If you go from here to here, you should have same thing. Then this should be multiplied by running wave, right? Then when you do the return, what do you get? If you multiply this one by this one, it gets distorted like that, right? You have the same function like this, so then it's coming like this, so then you have, right? You can see how this one is modulated by this period. So this is how it looks like. These are the localized wave function at each lattice point. Then you multiply by this one, you can see at each point, these are these potentials, right? This wave function. If you multiply by your this running wave, this is how you multiply wave. You know how to multiply two functions, right? So this is the running wave function. These are this tiny, this at each point. When you multiply, you know, because at this point they are smaller. When you go here, it is. So this is the block wave function. So this is the individual that UK function. This is the sine wave function. This is this function, right? These are this individual point at every lattice point. When you multiply these two, you get this point. This is how the block wave function looks like. It's not too bad, right? It shows that sinusoidal kind of function, except for these distortions. So if somebody wants to know what is the nature of your block wave function, this is the wave function. Is that clear? That's the multiple of two things, right? Running wave part and the periodic part at each point. Okay, so next one I will use block function. Oh, yeah, it's almost time. I'll talk about this one. Yeah. So then let's use block function to solve one example. Then we can introduce something called holes. Yeah, I'll stop here. Okay. It's your Thursday.